Welcome to this conversation. We have Gerald Friedland here with us. Gerald, thank you for joining.
Yeah, hello. Thank you for having me.
Yeah, and Gerald is employed as a principal data scientist at the Lawrence Livermore National Lab, and he's also teaching data science and AI at the Department of, the ECS department in the University of California, Berkeley. So yeah, thank you for joining us. And maybe we're going to, let's jump in. Sorry, I've got a train going by right now. Hopefully you don't hear that.
So quick update on this. I'm actually not anymore at Livermore, but I'm still teaching data science at UC Berkeley. So
all right, awesome.
Yeah, okay.
Yeah, so I just thought we'd have a conversation to discuss where you see machine learning going, and I guess what you're excited about and current research areas that you think are promising, and basically just kind of survey the field and get your opinions on what the future holds for deep learning, machine learning, artificial intelligence.
Yeah. So I think we are in a state of machine learning that's actually quite interesting, right? So we have a mainstream. So when I started doing machine learning, that was 2001, and it was not mainstream. It was, something you did as a homework, right? And I make the joke, backpropagation was a homework in 2001. And in 2020, it's a product by Google, but all the problems that we had in the homework weren't solved yet. Okay, so we just made it a product. And the interesting part here is that what happens is that we took a field that we almost didn't understand, or basically had very little understanding of, and decided we don't have to understand it. What we have to do is we just have to have empirical results. And then basically what happens is we decided, let's build a neural network, and oh wow, the accuracy is really high. Neural networks is cool. And then after a while, there was some criticism of neural networks, so it switched to support vector machines, because they had a lot more theoretical foundation. But then they had limitations too. And so then at some point somebody said deep learning. And so we all switched to deep learning and said, okay, it needs to be a deep network because deep is better than wide or anything. And that is after Kolmogorov had already showed in the 1950s that all you need is 3 layers. So why is deep better than wide? Nobody knows. But empirically, it seems to be the case. And what happened next is that we decided, well, because deep is better, so a lot of parameters are good, but that requires a lot of computation. So the industry the hardware industry that was hit by Moore's law, right? And because Moore's law was usually the original promise was every 2 years or so, your number of transistors doubles. So the industry was one of massive growth. If you remember in the 90s, we had to buy a computer every 2 years because after 2 years, computer was completely obsolete to the point that people would tease you about it. That's how obsolete it was. Now I have a Mac from 2012. It works fine, right? Why? Because and the hardware growth isn't there anymore because we reached physical limits. So now instead of the gigahertz going up, it's the gigahertz is the same. It's just the processors going up. And now the hardware industry needed to really search for opportunities to sort of massively use this parallelism. That's the only thing they could do. And because it's not trivial to parallelize things, and machine learning seemed to be one of the application areas. And so we have spin-offs like NVIDIA, right? Instead of just doing graphics, they also do a lot of machine learning with GPUs and so on. So there was a massive growth in that field without people ever stepping back and saying, okay, but really, do we need neural networks? Why is deep better? How does the whole thing actually work? What's going on here? What are we actually doing? And on top of it, also business is how important is it that we do machine learning in business? Many machine learning projects fail. They ended up being research projects for a year or two, and then there's not really an application, except in areas where prediction has been done for a long time, like insurance or stock, stock predictions. But in those two, turns out, the last time I have a lot of contacts there, nobody uses neural networks. They use random forest or time-based methods that are, a lot easier to understand. So what happened here? What happened here is yeah, we have a hype that's fueled by a bunch of hardware, and also by the idea that, oh, I don't have to understand anything, right? So just using an API that just does its thing is obviously much easier to understand than actually doing software engineering, which is also reflected in salaries. Software engineers get a lot more salary than data scientists. So how can we change that? What should we be doing? What is the future? What should we actually doing from now on? I think the first thing is to understand that model building has been there for hundreds of years. Computer science is not the first one who builds models, okay? The first one who built models of nature were the physicists. And unfortunately, as much as we sometimes hate them, the reality is they have a bunch of really, 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 really good ideas of how to build models efficiently so that they generalize, because they have developed those ideas over hundreds of years doing it manually. And we can learn from them stuff like Occam's razor. Like, it's actually not necessarily better to have the large amount of parameters and deep layers and complicated models that nobody understands. Simpler is better. And actually, we learned that in computer science too, with keep it simple, stupid. The KISS principle we used in programming languages. Why doesn't that apply to neural networks? Turns out it does apply. It's just not beneficial for the hardware companies. The hardware companies obviously like us to use a lot of CPUs. So it turns out if you start actually understanding what a neuron, for example, does, and put this into the scientific context of what a neuron is. So a neuron is an energy threshold. We have so many neurons, for example, all over our skin. We can't have all neurons fire all the time. No. What we do is we only fire when the brain needs attention. Like if I step on your left toe, you say, ow. Well, because some neurons from the left toe decided, oh, there's some energy that I don't know what to do with, so I need to signal your brain, right? Of course, we also think about our left toe when I talk about it because it's a simulation instance in our brain, but that's a different story. In reality, neuron is an energy threshold, and it switches on or off. So it's an energy switch. Turns out an energy switch is the same as if I took a transistor and put a little capacitor up front, just until you have to wait until there's enough energy so that the capacitor is loaded, and then the transistor switches through. Guess what? So there's an electrical engineering understanding of how to architecture neural networks already there, has been there for decades. It's just completely not taught, because why would we think about things like neural networks? They're magic boxes, right? And of course, when does this become important? Well, it becomes important when we want to understand something that, like, there's a generalization accuracy trade-off. Most people nowadays only measure accuracy and then hope that, high accuracy on the validation set translates to generalization. And that is often true, but not always. If you want it to be always true, then it's pretty clear that we have to reduce the amount of parameters pretty drastically in our network. And also then we go back to Kolmogorov and find out that 3 layers are actually enough. So why are 3-layer networks not performing as well as the deep layer networks practically? Well, it's pretty easy to think about when you start thinking about it. It's because the same you have scuba diving, you have 2 stages of air pressure reduction. Why wouldn't we just have 1 stage? It's easier, right? I just said it. No, we have 2 stages because engineering-wise, it's easier. If the first stage fails, the second can help it. So because learning is very hard, and in fact, backpropagation, even stochastic gradient descent, is NP-complete. That's been shown a while ago. So it's all exponential. So it's much easier to just halfway train the first layer, and then the second layer can correct, and the third layer can correct, and so on. That goes to a certain limit, because of course, if you have too many layers, then you have something that's originally called vanishing gradients, but now it's obviously nothing else but the data processing inequality. You can pass data through all these thresholds. At some point, you end up with nothing. And so all of these things need to be taught and understood in a way that they become an engineering discipline. And once we become engineering models, we can start making AI an engineering discipline. So where we actually say, okay, instead of just tinkering it out, hoping it works, we know exactly the size of the neural network that we need. We know exactly what we can expect from that. We know exactly sort of adversarial examples, which is nothing else but a contradiction to the generalization assumption. When do they come? Well, they come when you don't train to the end, right? So we can't always train to the end, but it's always obviously easier to train to the end if there's less to train, right? Or at least closer to the end. And so that's all of these sort of clearly teachable things that require a unified theory of these things. And it's all there. Okay, I don't think there's a lot of innovation that need to be done. Theory is usually written hundreds of years before we need it. So yes, I'm looking for, when I teach my class on experimental design of machine learning, what I looked at is, again, the original paper of the perceptron, right? Which is actually very interesting from Rosenblatt, because Rosenblatt ends his paper with, we should use information theory to understand perceptrons. Turns out, this is a very underappreciated comment, because there's the two major books that I know is, one is Thomas Cover, who has done work to understand neurons as information theory. And the other one is obviously David McKay, who is actually quite famous book. But unfortunately, all my friends have it in their shelf and never look at it. But the reality is, it's actually really nice. Once you read it and understand it, you feel like, oh, all of this makes sense now. All of these problems make sense, including problems like the curse of dimensionality is very clearly quantified there, really clearly explained. So it really is a notion where we went too quickly into a field and are now having to pick up, like, wait a minute, what we should be doing in this field is, let's not get rid of the enthusiasm or curb our enthusiasm. No, we just have to control our enthusiasm and use it for something which we call understanding. Because if we understand what we're building, then everything will get better, and then we can also defend it better when it doesn't work, or debug it when it doesn't work. Like, for example, the notion of debugging a neural network almost doesn't exist. If something doesn't work, I'll maybe try something else or spend more compute time. It turns out, when we tested different APIs of neural networks to their information capacity, it turns out that there were networks that actually cannot memorize. They're so badly tuned to not overfit that they introduce a bias that's unbelievable. So they actually cannot learn everything anymore, because the regularization terms are just like restricting it too much. I wouldn't use those frameworks. And it turns out, and I'm not saying names because I don't want to bash anybody, but empirically, all these practitioners found that out too. The practitioners were, don't use this, use the other one. No, well, yeah, because it doesn't matter if you find something theoretical that doesn't work, then actually practically it won't work either. And that's exactly what happened. And so, for example, when we did tests, something like scikit-learn, which is open source, it just works. And yeah, of course it does work, because it also, obeys all the theoretical, as close as you can get limits. Yeah, sure. That's why that framework is actually so successful. And it's the same thing, and has always been the same thing. So in short, we should take our enthusiasm and put it more into a engineering understanding of machine learning, and then from there on, the field will actually even flourish more.
Okay, so you're saying that these networks are far over parameterized, and so they can rely on hacks and cheats where they just correct with these subsequent deep layers rather than maximizing the theoretical limits of the parameters. I saw you actually had a custom version of the TensorFlow playground,
yes,
where you show the memory equivalent capacity of the neural network based on how many neurons and layers. And I actually found the cheat notes there kind of interesting and useful. The output, basically your calculation of how many bits it can memorize. It's additive in certain cases. And see the output of a single neuron. Yeah, very cool, very cool. I'm going to play with that more later.
I'm, for example, giving you an example of an exercise that is on my midterm in my class, and it's very practical. And the exercise goes like this: you have 1,000 videos that you need to classify into 5 age classes, right? TV everybody, TV 10 plus, TV 14, TV 18, and adult only, right? The typical rankings. And now the question is, not knowing anything about the task furthermore about the task is clear, but not knowing anything furthermore about the videos or the architecture you'll use, what is going to be the maximum amount of parameters that you can use before you risk overfitting? And it's interesting because it sounds like an absolutely hard to solve problem if you look at the current literature. But
before
it's actually
you risk
not.
overfitting.
Yeah. So it turns out it's super clear. It's 1,000 times log 2 of 5. Why? Because each video, once you classify video, that gives you certain information content, and it's log 2 of 5, because 1 bit of information is log 2 of 5 is how many bits of information each revelation of a video being classified correctly gives you. And now you have thousands of them, right? So the total amount of information that's in that table of 1,000 videos annotated with the 5 classes is 1,000 times log 2 of 5 bits. And now the interesting thing is that we know from David McKay that each parameter can easily memorize 1 bit of information of a perceptron. So what that means is maximally you need to use 2,300 parameters. And if you use more, you already risk that you're way overfitting. In fact, you already risk overfitting if you use 2,300 parameters. You need to actually use a lot less than that. And many people would say, wow, we're classifying videos, right? They're like a 4 gigabyte, like a DVD has like 4 gigabyte of data. So yeah, no, but it actually doesn't matter whether you're classifying videos or you're classifying words or you're classifying, whatever image features. It's never about the complexity of the input. I mean, it is because of the number of dimensions if you use a neural network. But in reality, it should be about the complexity of the input of the function that you're modeling. The function is from the video to the class, right? And so for that function, in fact, that's the complexity of that function, 1,000 times log 2.5 in bits. And that complexity metric, by the way, is not my invention at all. Claude Shannon in 1950s already asked, what is the complexity of winning a chess game? And of course, it creates a decision tree. And guess what? He used the physics notions that are different. But if you measure that complexity in bits, it turns out Shannon's number, which is, I think, 10 to the power of 120, if you take the log 2 of that, you end up with about 400 bits of complexity of winning a chess game. Now, 400 bits isn't that much. That's the entire game, right? So if you were in theory, looking at all the moves ever, that gives you 400, binary decisions. That seems like nothing, right? But the point is, that's the reason. It's actually nothing. It's very hard for humans, obviously, but computers were able to do that rather early. Chess computers we had pretty early, and also chess was the first thing we actually solved better than human, right? Where Deep Blue won against, and so this is how these complexity measurements actually help, because we see, is this task unsolvable, or is this task actually, actually 400 bits, that seems like it's not easy for human, but you can store a decision tree of 400 bits, especially on modern computers, right? And that's obviously why Deep Blue won, right?
So I guess what's the reason why the engineers would continue to overparameterize the network? Is it just difficult to discover the optimal parameter values using, just gradient descent if you have the minimum number of neurons required? Is it because we don't have like a dense enough sampling of the distribution space in order to smoothly, descend to those parameter values? And so we rely on more parameters and more layers as kind of a cheat around the lack of sufficient.
There are two answers to this that I in general give. One is, first of all, what is training actually doing? Okay, training is trying to solve a packing problem. If you think about it, you have your data set and you're trying to pack hyperplanes around your data set, right? So you basically, you're solving a packing problem. And now you can go ask any rental car company, right? If you go, let's say, and you move and you take a truck that's exactly the size of the furniture you have, then you have to pack that really tightly, and it has to be like, you have to find the optimal solution for the packing problem. That's why any rental car company will tell you, despite the fact that you think, well, they're incentivized anyway, use a bigger truck than you need it. And
Right.
I was always skeptical until I actually hired actual movers, and they said, no, you want to save money, you take a bigger truck, because the workload, the time of work is so much more expensive. Turns out, yeah, you take a bigger truck and then you can just put that stuff in, and has all kinds of holes, but at least you can move it. And that's exactly what happens these days. These holes are where we plug in adversarial examples. But the interesting part is that, yeah, if you don't want to solve the packing problem perfectly, you can find a lot of approximations, the bigger your truck is, pretty quickly, right? That's number one. That's a technical reason. And then there's a business reason. And the business reason is, again, NVIDIA and Google and Amazon make money when you need a lot of compute. So for them, it's actually better if the data structures are ginormous, and it takes forever. And GPT-3, for example, is a good example. I talked to Wikimedia Foundation, and they're actually almost figuring that the size of GPT-3 monopolizes Google, because it takes like $100,000 to train that thing. And so if this thing was smaller, then maybe it would actually be cheaper to train it. And of course, there's this trade-off, right? The trade-off is, wait a minute, didn't you just say it's faster if the truck is bigger, right? Of course I said this, but the point is, if I have to transport, let's say, my baby girl, I'm not gonna, and her like 5 things, I'm not gonna actually go with, a 7-ton truck. Then actually a small car is enough. And that's exactly the point. So we are not just over parameterizing a little bit, we're over parameterizing probably by an order of magnitude, if not 2. And that is the incentive that is, it's the compute incentive.
Okay. I know 3 days ago, Google just released the pathway language model. They're calling it PaLM, and it's 540 billion parameters. So
Right.
a couple times bigger than GPT-3. And it appears, though, from like the graphs they're showing, that, they're still getting, they think that scaling it larger would still yield an increase in accuracy. So they're showing that the accuracy is still scaling with the parameter count. So I guess maybe given backprop and SGG as a optimization process, I guess we're still getting these efficiency gains from parameters. And part of that could be deceptive loss functions, getting stuck in local optima. Whenever you have a high dimensional loss function, it's bound to be very deceptive in certain ways. In other words, following the gradient can actually make it overfit rather than make it generalize better.
And unfortunately, this is a very good discussion, and I think I partly agree totally with what you say. Unfortunately, this discussion on that level is very difficult to do, because language is also weird. Okay, so it turns out we think language is way more complex than it actually is. So, and in order to see, I don't know if you remember, but there was this little 20 questions game, right? And 20 questions, I can find any concept that you're thinking of. And guess what? That little 20 questions game was basically a key holder. It was part of a keychain, right? Little beepy LCD thing in the 90s. And actually, a neural network was used to train that thing. So how is it that in the 90s we could do a 20 questions game already? Well, it turns out languages isn't that complex. And I personally saw that. So I built a little robot. Another thing that I built a while ago was called a Movie. It's a speech recognition, an Alexa type of thing that you connect onto the Arduino, and it doesn't need the internet. I showed that the usage of the internet for Alexa and for Siri was, especially in the beginning, mostly to gather data from people rather than need it, right? Because also the easiest way to see that was the PlayStation 4 already had speech recognition capabilities and it used the cloud. When the PlayStation 4 itself had more compute power than the research clusters we used for actually speech recognition research, like 10 years earlier. So they could totally do it even on the site, on the machine. But they wanted to collect the data. But the interesting part there was that I built a little robot and I put it in a Maker Faire. And I was really concerned. I was like, if people talk to the robot, they're going to ask all kinds of questions. So what I did back then, I took the top 100 questions and answers from Alexa that were actually published on the web and just trained the robot to actually do those 100. And the interesting part was that over the 3 days of Maker Faire, we really literally had hundreds of people coming to this booth. I used about 5 or 6 of those top phrases. Turns out people are not nearly as creative as we think. And the funniest anecdote to finish that anecdote was that I went on my lunch break and met an artist, because also Maker Faire has a lot of artists. And I told him the story. It's like, I was so scared that people would ask things that it doesn't know, and it's embarrassing. But it turns out I programmed the 100 sentences and they don't even use all of them. In fact, they use like 10% of them. And he goes, well, who's the robot then? Right? And I was actually smart, which is totally right, because language is weird. We only use about 4,000 words all the time. And of course, a lot more words exist, but we just don't use them. And so I'm pretty sure we are overfitting manifold in GPT-3 and also the new model. But also, it could be definitely probably 2 orders of magnitude smaller. But also, we don't even know. Maybe they're just memorizing the entire internet in some ways, right? It's Google. Because I had another anecdote here. So a friend of mine collected back a while ago the 1 million song corpus. It's actually, you can Google that, still exists. But at the time, 1 million songs was actually a lot. So it's all commercial songs basically that have been recorded and commercialized. And 1 million is probably not every song, but it's a huge part of the songs. And the funny thing was there that I said, and we discussed this, is actually not so nice, because what if you just overfit the 1 million song corpus? It's a pretty good search engine. You don't need to generalize anything, because you can find pretty much any song you can think about already in the 1 million songs. And so that is the problem. So it's very hard to discuss. Language is weird, so there's a sort of an unfair advantage in this space. And so it's very hard to discuss how neural networks, for example, behave in that space, because the space is hard to understand. If you want to understand neural networks better, it's actually, and that's what I do, usually you use synthesized data and you really find out, for example, you use completely random data. And then with completely random data, you can actually find out, because there's no generalization with completely random data. The only thing the network can do is memorize. So can it memorize, testing on the training set? Can it memorize the random data? Then how much information can actually be memorized, and how well your backpropagation actually goes to that memorization and how fast, right? And then you can start changing the amount of randomness. For example, you could make one column dependent on another column, and you can see, does the neural network actually find that correlation, and so on and so forth. That is usually a way better way to understand how these networks behave, because again, especially in language, there is a lot of sort of extraness in there that makes it hard.
So in this case, I guess the human brain is quite overparameterized as well, right? We have 86 billion neurons, but if you count the synaptic connections, we're at 100 trillion or something. And so I guess the human brain is capable, obviously, of a lot more than what we use it for if it were trained optimally. And maybe part of that is to kind of offset the continuous learning problem. In a sense, we don't receive our data IID, right? So a lot of times, a lot of times, when you're looking at this from a theoretical standpoint, we're looking at this from like a spherical cow type perspective, but given real life constraints of continuous learning over the course of a lifetime from childhood to adulthood, how do you think that trade-off is changed if you don't get your data IID, if you have to encounter that in a very continuous fashion, and then do you have to partition the network and segment, and you also have to consider catastrophic forgetting, not overriding the classes that you've already learned, and then the unsupervised aspects of it probably increase the difficulty, right? Because in life we don't get our classes pre-labeled with every sensory input. We have to infer the classes. So we're doing our own, k-means clustering or something on our input data, and we're actually discovering the classes at the same time we're learning how to classify. So I'm really fascinated by what you think might be the path or the algorithms that might get us more towards that human-like.
Yes. So
learning.
So first of all, a couple of micro answers and then a macro answer. So catastrophic forgetting, for example, only happens if you overcapacity, right? So if you try to learn more than you have capacity for, obviously the network has to forget something, right? That's also why it's important to consider capacity, not just for the overfitting, but also for the opposite, right? That's number one. Number two is, that learning problem that we do in the brain is slightly different because it's kind of like reinforcement learning. We're using the neurons while we're training them, right?
Right.
This is why we need this very long bootstrapping process. Now, I wouldn't go for anything. So a couple of things we need to consider though before we go there. So first thing, talking capacity again. We actually cancel connections, okay? And you can easily see this because a baby will remember all the details of everything, right? So, it's like, and also learn super quickly. Giraffe, bum, memorized, done. So, and then everything is a giraffe, which is also interesting. Now, an old person, like, this 80-year-old grandpa, I don't know, just trying to stereotype it a little bit so we can use the example, is going to give you these high-level, wise recommendations that have nothing to do with details, that are all like, oh yeah, wow, this is sort of the lesson learned, the conclusion, the high-level advice. I mean, this is also the stereotype of a professor, right? It gives you the high-level advice, but you have to figure out the details, and that's exactly that. It's killing neurons, right? So over age, sorry, not neurons, connections. The over age, the irrelevant, pruning. The less relevant connections are pruned, and we only keep the big ones, which is basically the same thing as sort of eliminating the lower significant bits and only keeping the higher significant bits, right? So that's how this feels. So it's a relevance compression that's going on there.
Right.
So that's number one. So number two is—
I saw your video talking about how compression is generalization. Yeah.
Exactly. Yeah.
Right.
And you see that from lots of angles. And the second thing is the neural network itself, actually, we have to remember, is a function approximator. So it's maybe not the exact right model to think about in the brain, even though obviously we call it neural network. I think a better model for brain is something like the Hopfield network. So the Hopfield network is unsupervised. And a little anecdote here, which might be interesting for your YouTube viewers, is that Hopfield actually recently released a paper together with Krotov. Yes, the Hopfield network just turned 50. The Hopfield network, the person at Hopfield is much older. He's a physicist at Princeton University. He's actually the PhD advisor of McKay. So, just noting all of these connections. The Hopfield network, the Krotov paper was really interesting because he asked himself one thing. One thing was the original learning function was very simple in the Hopfield network, the Hebbian learning. And of course it was because back then, 50 years ago, computers weren't as powerful. So he was wondering, what if I use a more complicated learning function? And the paper is about that. And it's basically asking, yeah, you know what? If you do that, we just overfit quicker. It doesn't actually help. So a simple learning function will do it. In the same ways, it's interesting because the Hopfield network, he can actually solve Cipher 10 without looking at the labeling. Turns out you can classify, you can solve classification tasks like Cipher 10 with Hopfield networks, but they're unsupervised. So the labels don't matter. It's just in the end, you have 10 classes and they just label, of course, the prototype of each class, which would save so much work in labeling if we made that happen. Yeah, there's obviously something higher level there. And that is obviously that the brain, like anything else, is nothing else but doing entropy reduction, right? And so there is actually a universal rule that everything follows anyway. But that's a little bit too high level because we got to know how, right? Yeah,
right. So given that we have this gradient descent as our primary tool in our toolbox, and we're using it with very overparameterized networks, and that compression is how you get to generalization, then I guess the architecture that comes to mind is something like a variational autoencoder, where you could compress your data. You could learn a model of compression down to a very small bottleneck, and to create a very, succinct vector encoding or embedding.
I like variational autoencoders for that analogy. It's basically a nonlinear PCA,
right?
Which is, by the way, a problem. People worked on so long to try to find out ways to do nonlinear PCAs, and I think a variational autoencoder is the solution to that. I think it's just good to mention that. I think, it's people like clicks for them, hopefully. But yes, this is true. A variational autoencoder would be very similar to Hopfield network in that sense, that it just tries to just reduce the dimensionality in the right way. And and I think these are the future. I think this whole labeling game over a long time is not the future. The future is to really get rid of that and just figure out how to do this automatically. And the interesting part is, when we look at this today, then this points us to other interesting areas that in some way work similarly. I can't explain it, but it's like quantum computing, for example, is obviously in some ways similar, because you have a field that and a beam, and it automatically needs to figure out how to reduce things, and there's a lot of analogies left and right that all point to like, there may be just one universal algorithm that reduces information. And there's like, it's hard, obviously, if I would find it as a universal theory, but it's very clear to me that there's probably a universal algorithm that reduces information just like the brain does. Okay. Here's what's interesting, however, and this is going back to your original question. You're saying the brain is overparameterized. I believe that too, by the way. But my answer to that is, evolution isn't perfect. And that is the difference. When we build neural networks from scratch, we shouldn't make evolution's mistake. It's the same thing. When we built airplanes, initially we looked at birds, that came out of evolution. But now we can build airplanes that, fly Mach 2 and transport 700 people. No bird can do that. So we should be ending up better than sort of the evolutionary structures that we see, right? So.
Yes, and if you compare where we're at, if given huge corpuses of data, we can get there with lazy, computationally inefficient methods right now in certain types of tasks. But then there are other areas where it seems like we're a long ways. Right now, for the last 10 years, it's fair to say that almost all of the effort in the industry has been on the supervised learning. It does seem to be shifting over the last few years more towards self-supervised metrics, just because supervised labels are always so low information. If you look at the actual label, you're talking some binary value. It's something that you can feed in as a one-hot encoding or something. But when you go to unsupervised, now you have a much richer labeled data set, because your data becomes the label part of it. And so you have a far more information to work with in terms of what your labels are. So I think self-supervised is continuing to make a lot of progress. Obviously, in language, it's all the last few years has been a story of self-supervised with these transformers and autoregressive models that just complete the.
And I think it's a great idea to develop those with language first, because language information density isn't actually that big, that great, and it's also very intuitive to see the output, right? GPT-3's output is super nice to look at. It's like, oh yeah, that's intuitive. That makes sense to me, right? That's important. While if you try to do that on some problem, like, I don't know, like customer sales or whatever, then it's hard because you don't know if the solution is right. So I think.
And it becomes way more difficult as well with like video, where you have a higher dimensional space with a lower information content per bit. I mean, I think, Claude Shannon calculated the English information density, and it has some redundancy, but it's actually quite efficient in terms of being a good communication protocol. So we're going to be making networks multimodal as well over the next few years, and that has a whole new. I mean, that's basically where we can see another 10x probably
Yeah, and I think going multimodal and also going super high dimension, that's where you need to understand things. That's why my research has been in that space. Because, it's kind of funny because, and they're right. Like if you ask a statistician, they say, well, just use regression. True. If it's a low dimensional problem, I agree. Let's use regression, or let's actually do it manually. Come on, right? Just look at the data done, right? The good old plotting does help a lot. But once you get to, like, let's say genomics, and you have 150,000 genes, and you want to know which two are responsible for the type of cancer, good luck visualizing that. That's
Right.
where you really need to know. But then also you need to know that you don't just find random columns because you were lucky, or you don't want to make sure that it's not too noisy that you don't find anything, right? So then you have to really start to understand things. And then the tool that I've been developing over the last 2 years called Brainome, we actually start to use information measurements to build machine learning, and to also sort of do so for causality with ranking. And the interesting part about that is that, yeah, we have no problem. And we just worked with Microsoft Genomics and different other people as well to just find genes just in that way. And yeah, it works like it does its thing in minutes when other people like can't even load the table, right? Which is really nice because we can just measure things out. We measure things out like an engineer measures a bridge or a kitchen or whatever before we build something. And I also completely agree. I think I heard this a little bit in your questions, that yeah, we are kind of a slave of stochastic gradient descent right now. Like this is just really holding us up, that we still have to use this. And you could say, well, it's NP complete. Unless you solve P equals NP, you can't do anything about it. That is true, but we just have to rethink the whole problem. And one way to rethink it is to not start with, okay, here's a neural network, let's train it, but to build the network neuron by neuron by neuron by neuron. And that's actually interesting because, for example, perceptual learning, so the individual neuron learning, is actually mathematically rigorous, and we know it converges to a global minimum. Perceptual learning is proven to converge. And it's interesting because, wait a minute, why did we actually abandon this? We abandoned this because Minsky didn't know about capacity. That's the real reason. He was telling us, well, a neuron can't even do XOR. Well, yeah, XOR requires 4 bits of capacity, and a single neuron for 2 inputs is only 3 bits of capacity. So yeah, we can't learn XOR. But we can take a data and know how much information we can handle, and then say, okay, there's more information, so let's add another neuron, let's add another neuron, let's another neuron, and we can come out with new learning schemes where maybe we do perceptual learning for each of them, and then we just have to figure out how to do the last neuron, and so on and so forth. Because the last time I checked, every engineer on Earth loves Lego. That is putting piece by piece together to build something up, right? Nobody takes scrap and just models it and hopes that it can bend the right way, because that's the way we do machine learning right now.
Yeah. Yeah, and it is cool that we're going to be able to compose the neural network outputs are going to be fairly composable. Like if you think about taking different sensory modalities and creating an autoencoder, a variational autoencoder compression, and then take those compressed dimensionality reduced embeddings and use those vector embeddings as the inputs to other networks, then you get to be building more complex structures with.
I mean, I completely agree. That is the nice. We really we start to understand how the information reduction. I mean, the machine learning community is getting there. It's just, I wish we would start also a direction away from stochastic gradient descent, and people trying to propose
moving away from stochastic gradient descent. I think one of the biggest things that I see is that it really fails when you have deceptive loss functions, and the higher dimensionality of your data,
exactly,
the higher dimensionality of your data, the more guaranteed you are to have deceptive loss functions.
Mm-hmm.
I mean, imagine just a single 2-dimensional maze, and how many ways gradient descent is going to find traps, or different ways to get stuck in in different structures there, but then make that high dimensional, right? And now optimization, sometimes And there's two researchers that I really love, Jeff Clune and Kenneth Stanley, that are developing the thought around why this is the case and solutions to it. They're looking at more novelty-directed exploration, because if you look at what got to a human brain, it was an evolutionary algorithm that was creating not just one organism, but in a single run, the evolutionary algorithm created millions of different species, and it did so because each species occupied a different spatial area, and so these species were able to kind of co-evolve in parallel. And so you have in our four-dimensional space-time, you have a four-dimensional discretized space where we have organisms evolving in parallel, and it's a parallel search process. And sometimes you have extinction, which frees up the environment for a new species to move in. Sometimes you have, genetic drift, you have recombination in certain cases. And it's the parallelization of that search process and the fact that it's evolutionary rather than direct optimization that kind of so evolutionary algorithms can definitely succeed where stochastic gradient descent cannot, in the sense that, and especially when you do what they call a quality diversity search. So you're actually making one of your objectives diversity itself. So you could take, for example, your parameter space, and you could look for networks and look for multiple networks and populations of networks. You could combine them, but then one of your criteria could be that you're looking for networks that are far away from each other in vector space, right? So you're looking for the diversity, not just the convergence. And I feel like that's an underexplored part of this industry right now.
I completely agree with that, actually 100%, because the genetic algorithms are extremely powerful, especially they were kind of abandoned again for computational reasons, but we have to revisit all of them because computation is now the big thing. But the other thing is, actually, it's interesting because even that was predicted by David McKay. He has a chapter, and this is super interesting. I looked into this very shortly. He has a chapter, I forgot which number it is, but you can look it up, and it's called "Why Have Sex?" And don't worry, we'll keep this PG-13 here. The point is obviously not the answer you think. The question is, why does nature want this complicated process of two individuals finding each other? And every human knows how difficult that is, finding each other and then reproduce, rather than, for example, a plant. You could just take a branch of the plant, put it in the soil, and you have a new plant. Or an amoeba or a bacteria will just divide. And it turns out there's an information theoretic reason for it. The information theoretic reason is that you can, if you're an amoeba, you only have one bit of adaptation per generation. So asexual reproduction gives you one bit of adaptation, while sexual reproduction gives you square root of G bits per generation, but G is the number of bits in the gene pool. And of course, that's a lot of bits, and square root of that is still a lot of bits per generation. So we can afford to wait, let's say 25 years until we reproduce as humans, while the amoeba needs to do it every 15 seconds. And if you now do the math, you'll find out that actually most species have about the same bandwidth of adaptation to Earth, because that's probably exactly what the Earth demands for us to be adaptable with in order to survive as a species. And of course, we humans are the only ones who supersede that adaptation, right? But not by genetic reproduction, no, by obviously what I call the brainome. Because the brainome is something that is an adaptation mechanism that other species rarely have. Maybe wolves have a little bit of this. The brainome is the following. We have a virus like COVID-19 attacking us. And of course, each one of us wouldn't be able to do anything about it. Maybe, we can wear a mask, literally, right? But together as humanity, we were able to create not just one, but like 5 or 6 different vaccinations for it within, 18 months. And that means the virus doesn't actually attack just the individual, and the individual then has to react to it. The immune system is genetic, right? That it can do so much, right? Our neural system is day to day. It can do something, but not everything. But the combined neural system actually is able to completely outperform the adaptation of the virus. And of course, it's still difficult because it mutates and we have new variants. That's the whole point. That's the game. But we are able to basically outperform the virus in adaptation by using combined brainome. And I actually have, I created this word brainome because we don't even have a word for this. We call it culture usually, right? But culture is so political. It's like, German culture versus US culture versus, I don't know. No, brainome is China, Russia, they didn't care. They wanted to just kill the virus, right? That's all our brains together. And ultimately, that's an adaptation that is awesome, to fight a pandemic. But it's very bad when we then forget that we also over-adapt in the sense that instead of finding a cave to, just survive, we built houses and we overpopulate because we're so successful. And then, of course, we create issues like climate change and other things. That means with our adapting more than the environment requires us, we actually start to adapt the environment to us. And that results in a responsibility, because if we overdo that, then we may adapt it in a way that we can't survive in it anymore. It's kind of weird. Yeah.
Wow. So fascinating ideas there. One being that sexual reproduction is more efficient than asexual or parthenogenetic reproduction. Yeah. And then the second idea is the importance of the communication between the multi-agents in the population.
Exactly.
And the sharing. And so almost what you might call a memetic evolution of ideas that has enabled modern society, because we're not, in fact, without our society, we would all be probably very, almost no more intelligent than any other great ape.
Maybe an elephant or a whale or something like that. Yeah.
Yeah. Without the benefit. In fact, it's really humbling when you realize that without language, which is this memetically evolved encoding of like vectors to different thought patterns, without language, we wouldn't be able to even run an internal thought dialogue. Yeah. And when you realize that your internal thought dialogue depends upon you having learned language encodings that were words developed thousands of years ago by other people, you're like, wow, this language thing that has evolved with our species, this memetic encoding is so integral to my own thought process. Yeah. Would I even be able to hold a thought? Or if I didn't have language, would all I have is feelings and no thoughts? Yeah. Because definitely your vocabulary, like you said, we use a much smaller vocabulary in everyday than we need to. And there's this much richer vocabulary, and the more vocabulary you have, that expands, I guess, the number of tokens that you have to represent thoughts internally, or the vocabulary of your token index. It's incredible when you realize that without the memetic evolution, we probably couldn't even run a thought in our own mind.
Yeah, you wouldn't know about math or anything, right? I mean, all of this is you learned in school. But school is interesting because it's actually exactly that. It's the formalized training of the memetic evolution, right? So we make this such that, we're better than evolution, right? And I mean, the final thought, the thought that I usually give people is like, it's really funny. If there was only a way to cheat evolution and to actually increase our lifespan, and that would be super cool. Turns out, it's called science. Because that's actually what science does, right? Yeah. We are actually, that's the whole point. We are just formalizing this sort of memetic evolution and thereby making the thoughts sharper and more compressed, and thereby actually accelerating it even, right? Because societies will find things anyway. I would think, you probably could discover pretty much everything you wanted anyway, but by making it formalized, it becomes even faster. You know exactly, now you say, okay, he's the expert in this, he's the expert in Y. Well, that makes communication easier. You know who to address. And then also they can have conferences that are just in the field. They don't have to talk to everybody and so on, which makes the whole thing just even more effective. the memetic evolution, which is, you could say, optional, right? We will survive anyway, but then again, it's kind of really nice to have it. And so let's let's keep culturing it. And the other thing is that science is really bound to the truth, and that's whether people like it or not. I mean, we can err, obviously, but I would say, first of all, we are able to update always. And the second thing is, we err despite the very best effort, okay? That's the point. Yes, it errs, but you will err more often with other methods, right? Science really is the thing that helps that memetic process. And I'm always very sad when science has to give way to power or to other things that shouldn't just impact the truth. I always feel like if you want to exert power, there's other ways. You don't have to make science bad for that. I mean, this just makes no sense, but that's my personal feeling.
So if we were to define a hypothetical training environment where you would attempt to evolve some kind of more generally intelligent algorithm, I think it goes, so what are the aspects of that would be most critical? So I think something like sexual reproduction or some kind of genetic transfer between members of a population makes sense. Having multiple populations makes sense because it's not guaranteed that any particular clade or genetic branch on the tree of life is going to not get stuck in a local optima. Obviously, something like a mosquito is in a local optima for its niche genetically. And because it's in that local optima, it's unlikely that given any amount of time, a mosquito would ever evolve into something approximating the generality of human intelligence, right? Because they're so trapped in the local optima of being a lightweight insect that to escape the energy, to escape that local optima is probably unlikely to ever succeed. So there's certain local optimas that are stronger traps than others. In other words, you have more energy required to escape that local optima. And a mosquito seems like an example of something that's really stuck in a local optima. It's unlikely that given another 5-10 billion years of evolution, a mosquito would ever have progeny that ended up doing computer science.
Exactly.
Right. And so, but in order for evolution to discover all of these species, part of what it needed was this like a discretized space. So if you took your parameter space and you only allowed surviving populations, and let's say you took 4 or 10 dimensions of discretizations, and then 4 or 10 dimensions of parameter space, and then you discretized inside of that space, and then you allow populations to exist in each unit of that space. Or let's just be simple, three dimensions, and you have 27 units. Then in each of your 27 subcubes, you can have one population of agents that would be like a clade, and they would genetically reproduce. And then potentially you could even allow for like some cross pollination and cross sharing of genetic material, which I guess happens all the time with bacteria, right? They bump into each other and they share little aspects of their genome. Well, obviously the eukaryote moment is a pretty significant point in evolution. But then they need to also be able, the agents need to be able to communicate. So there needs to be some kind of a compression and communication protocol between agents where they can request information and then share information in a way that they can edit the model. So without language, it's unlikely that we would have any of this intelligence in modern society that we have.
Exactly. And yeah, that's exactly right. And I think, so just to quickly respond to this, I think evolution has been created by evolution. Okay, so this is kind of like, you got to think the meta level. If we start engineering evolution, which is sort of what you're alluding to, right?
Right.
Yeah, once we succeed with that, it's gonna be brutal. That's the thing I fear. Because unless we bring a fallback switch back there in, it should outperform us. Because just like if you had a race between a bird and a jet plane, the jet plane will win. Right.
Yeah. So this is an intriguing thought experiment I've considered. One is I don't know that we get to AGI without some evolutionary search. It's the only algorithm that we have an existence proof that works because it's somewhat immune to deceptive loss functions, at least more immune to them than gradient descent, which follows the deception all the way.
Yes. But it's trying to approximate a function also, right? The function in evolution changes all the time. That's the problem. Otherwise, we would just converge to something, but we don't. Nature changes all the time.
Right.
Yeah.
And so the other scary aspect of using this is that it seems that all of our selfishness and our ego as a human species is the product of the rivalrous genetics that we've inherited, because predation and selfishness is encoded into our very nature, right? And so it seems that two things are true. Number one, we won't get to AGI without evolutionary search, and two, evolutionary search predisposes your model space to have an ego and a sense of self and a desire to advantage yourself at the cost of other agents. So in a world with agency misalignment, where everyone can externalize a cost to others at their own advantage, it seems like the the only path to AGI is one that unfortunately creates agents that actually do have their own interest at heart.
It's that's to be I mean, that seems to be the observation and to be proven. I have to unfortunately go. I have another meeting right now, but awesome. That was very fun.
This has been a fun chat. Maybe we can do it again at some other time, and I will let you go. And thank you so much for your time.
Thank you so much. And, let me know. You probably cut it together in some way, right? So,
Yep. I'm just starting this out, but thanks again. And
thank you.
It's been